Far out on the cold edge of our solar family, two pale blue worlds drift in near silence, so distant that sunlight reaches them as little more than a memory. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. These two worlds are Uranus and Neptune, the ice giants, and they remain the least understood of all the planets that circle our sun. Picture yourself drifting outward from the warm inner worlds. You pass the rusty deserts of Mars. You glide by the great striped clouds of Jupiter, and then the soft golden rings of Saturn. The light grows thinner here. The sun shrinks to a bright pinpoint, no longer a disk, but a single brilliant star among many. The space between things becomes vast and quiet in a way that is hard to imagine from the surface of Earth. And then, slowly, a smooth blue sphere appears in the dark. This is Uranus. It is a soft, even pale cyan, like still water under a winter sky. There are no bold stripes, no swirling storms easy to see. It looks calm, almost shy. Its color comes from methane in its upper air, a gas that drinks in red light and lets only the cool blues escape back into space. Continue outward, and the sun shrinks again. After a long stretch of empty dark, another sphere appears. This one is deeper, richer, a brilliant cobalt blue. This is Neptune. It glows with a color so vivid that it almost seems lit from within. Its clouds move in long, pale streaks. Faint, dark spots come and go in its upper air. It is the farthest true planet from our sun, and the most distant world we have ever visited up close. Both planets are giants, though they are smaller than Jupiter and Saturn. You could fit about 60 Earths inside Uranus, and just under 60 inside Neptune. Yet, they are not made of the same stuff as the larger giants. Jupiter and Saturn are mostly hydrogen and helium, the lightest gases. Uranus and Neptune hold a great deal more water, methane, and ammonia, all in strange forms shaped by enormous pressure. That is why we call them ice giants, though the word ice here means something far stranger than the ice in a glass of water. We have only ever sent one spacecraft to either of them. A single visitor, Voyager 2, swept past Uranus in 1986, and Neptune Each meeting lasted only a matter of hours. Then the probe sailed on into deeper space, and the ice giants returned to their long privacy. Everything we know about them up close comes from those two brief encounters, plus distant glimpses from telescopes near Earth. It is a small library of knowledge for two enormous worlds. This is why so many open questions still hang around them. We do not fully understand why Uranus lies tipped on its side, rolling along its orbit like a marble. We do not know why Neptune gives off more heat than it receives from the sun, while Uranus seems strangely cold for its size. We do not know what their deep interiors are truly made of, or whether liquid oceans hide beneath their clouds. We do not even know exactly where they formed. Some researchers wonder if they were born much closer to the sun and slowly drifted outward over millions of years. The mystery you are settling in with tonight is gentle and very large. Two pale blue worlds turn quietly at the edge of our sun's reach, and we still cannot say with confidence how they came to be, how they work inside, or what secrets their moons might hold. They are close enough to study and far enough to remain almost untouched by our eyes. In the sections ahead, we will drift among their faint rings and their odd, scarred moons. We will sit with the strange idea of diamond rain, falling slowly through layers of dense hot fluid. We will listen to the silence of winds that move faster than sound. We will wonder about hidden oceans, tilted magnetic fields, and seasons that last longer than a human life. And through all of it, we will keep returning to the same soft, open question. What are these two pale blue wanderers really like, deep inside? And how did they come to rest so far from the warmth of the sun? For now, settle in. The sun has shrunk to a star. The dark is wide and patient, and two quiet worlds turn slowly in the cold, waiting for us to understand them. Before there were telescopes, there were 6 planets. That was the old count, settled for thousands of years. Mercury, Venus, Mars, Jupiter, and Saturn, plus the Earth beneath our feet. People watched them move against the fixed stars and gave them names from old myths. The list felt complete. No one expected another world to slip into the family. Then, on a quiet spring night in 1781, a careful skywatcher named William Herschel was sweeping his telescope across the stars. He noticed something that did not look quite like a star. It was a small round disk, faint and green-blue, sitting where no planet was supposed to be. At first, he thought he had found a comet. Other astronomers checked his work, traced its slow path, and slowly came to a stunning idea. This was a new world, a seventh planet, twice as far from the Sun as Saturn. We had been missing it the whole time. That world is now called Uranus. It is enormous by human measure, though small for a giant planet, about 4 times wider than Earth. If our planet were the size of a tennis ball, Uranus would be roughly the size of a basketball. You could fit more than 60 Earths inside it. And yet, it is so far away that the Sun, seen from its cloud tops, looks like little more than a very bright star. Sunlight there is about 400 times fainter than the sunlight warming your window at noon. The story of Neptune began differently. Neptune was not stumbled upon. It was predicted. Astronomers in the early 1800s noticed that Uranus did not move quite the way the math said it should. Its orbit wobbled just a little, as if something else were tugging on it from farther out in the dark. 2 mathematicians, working separately in France and in England, calculated where that hidden tugger ought to be. In 1846, a German astronomer pointed a telescope at the predicted spot and saw a small blue disk on the very first night. It was a triumph of pencil and paper. A new planet found by arithmetic before any eye ever saw it. Neptune is just a touch smaller than Uranus and a little denser, about 17 times the mass of Earth, where Uranus is closer to 14. They are near twins in size, both far smaller than mighty Jupiter and Saturn, and very different from the rocky worlds closer to the Sun. Neptune sits at the true edge of the planetary family. It orbits at about 30 times Earth's distance from the Sun. A radio signal from Neptune, traveling at the speed of light, takes about 4 hours to reach us. The same signal from the Moon takes about a second. Their composition sets them apart from the gas giants. Jupiter and Saturn are mostly hydrogen and helium, the lightest stuff in the universe. Uranus and Neptune are different beasts. They hold hydrogen and helium too, but deeper inside, they are thought to be rich in water, ammonia, and methane. Astronomers call these substances ices, not because they are cold and solid like the ice in your freezer, but because they are made of light elements that freeze easily in the outer solar system. So we call Uranus and Neptune the ice giants. The name is a little misleading. The interiors are likely searing hot and crushingly dense, more like thick, glowing fluids than anything you could skate on. Both worlds are old. They formed alongside the rest of the solar system, roughly 4.5 billion years ago, from the same swirling disk of gas and dust that built the sun. But how exactly they grew so large, so far from the sun, in a region where the disk was thin and cold, remains one of the open questions we will sit with later. There simply may not have been enough material out there to build them in the time available. Some researchers wonder if they formed closer in and then drifted outward. Others suggest the early disk was richer than we think. The honest answer is that we are still working it out. For now, hold the simple picture: two pale blue worlds at the far edge of our sun's family. One found by accident through a backyard telescope. One found by mathematics before any eye confirmed it. Both enormous, both ancient, both made of strange, warm ices we do not fully understand. Both visited so far by only a single passing spacecraft. Beyond that brief glimpse, almost everything about them remains a quiet, lingering question, waiting in the dark for someone to come back and look again. Of all the worlds that circle our sun, none lies on its side quite like Uranus. Every other planet spins more or less upright, like tops set turning on a flat table. Uranus rolls. Its axis tips over by about 98 degrees, so its poles point almost directly at the sun and the distant stars in turn. To picture it, imagine a globe knocked onto its side, still spinning, drifting slowly through the cold dark. No one is certain how it came to lie that way. The most common idea is a collision. In the early days of the solar system, the space around the young sun was crowded. Rocky bodies, the size of small planets, drifted through the same lanes, pulled and pushed by gravity. One of these bodies, some researchers wonder, may have struck the young Uranus with tremendous force, a blow like that could tip a whole world over, the way a hard nudge can topple a spinning coin. The impact would have happened slowly, in the way space events unfold, vast, silent, and final. But a single giant impact is not the only possibility. Some models suggest that two smaller collisions, spaced out across millions of years, may have done the work together. One strike alone might leave certain telltale signs in the moons and rings, signs that researchers have not quite found. Two gentler blows in this picture would tip the planet without scattering its family of moons too far. The evidence is incomplete, and the math still has rough edges. There is a softer idea as well. In this version, no great collision was needed. Instead, the slow pull of a passing moon, long since lost, may have tugged the planet over across many millions of years. A large companion drifting just so could have wobbled Uranus more and more until it lay on its side. This is sometimes called a resonance, a steady gravitational rhythm that builds tiny effects into very large ones over time. Whether such a moon ever existed is still an open question. To understand any of these stories, we need to step back to the planet's birth. Around 4.5 billion years ago, the Sun was a young star surrounded by a swirling disk of gas and dust. The inner part of the disk was warm, and only rocky worlds could form there. Farther out, where the cold lived, water and ammonia and methane could freeze into tiny grains. These icy grains stuck together. They grew into pebbles, then boulders, then mountains, then cores the size of small planets. Uranus grew in this cold zone, gathering ice and rock around itself. Once it reached a certain size, its gravity began pulling in hydrogen and helium gas from the disk. But the gas in that outer region was already thinning out, and the young sun was beginning to blow it away. So Uranus never grew as massive as Jupiter or Saturn. It became a different kind of world, heavy with ice and water, wrapped in a thinner cloak of light gases. This is why we now call it an ice giant rather than a gas giant. The exact place where Uranus formed is another open question. Some studies suggest it may have been born closer to the Sun than it sits today, and only later drifted outward to its present orbit. Others propose the reverse, that it formed even farther out and slid inward. The truth may be a mixture, with the great planets shifting back and forth in their early years like ships finding their anchor. If Uranus did tip over from a collision, the timing matters. It probably happened after the planet had already grown its main body, but possibly before some of its moons had fully settled. This could explain why those moons now orbit around the tilted equator, as if they had been swept up into the new arrangement. A late impact might have stirred everything together: the planet, its rings, its small companions, into the sideways system we see today. What we are left with when we stand back and look is a world whose birth is still half hidden. We know the cold ingredients. We know the rough age. We know that something unusual happened because the evidence of that tilt is undeniable. But the exact blow or the exact dance of gravity that laid Uranus on its side remains out of reach. The clues are scattered across billions of years and trillions of miles. So tonight, the planet rolls quietly through the dark, carrying the memory of its own beginning. Somewhere inside that slow turning is the answer to how it came to be this way. We have not yet found it. Neptune glows with a deep, dreaming blue, the color of a sea that has never seen a shore. From a distance, it looks almost peaceful, a single round sapphire turning slowly in the dark. But that color is a clue, a soft signal pointing inward to the strange recipe that makes this world. To understand Neptune is to ask a simple question with no full answer. What exactly is it made of? The outer layer is mostly hydrogen and helium, the two lightest gases in the universe. These are the same gases that fill the sun, the same ones that filled the cosmos soon after it began. Every breath of Neptune's upper sky is, in a sense, ancient. Those atoms were forged in the first quiet minutes after the birth of everything, long before stars, long before planets, long before the idea of a sky. Mixed into that pale hydrogen air is a small amount of methane. Methane is a simple molecule, one carbon atom holding 4 hydrogen atoms close. It is the same gas that bubbles up from marshes on Earth, the same gas that drifts through the rings of distant comets. On Neptune, methane does something quiet and lovely. It soaks up the red light from the sun and lets the blue light scatter back into space. That is part of why the planet looks so deeply blue. But only part. Researchers still wonder why Neptune appears richer and darker in color than its sibling Uranus, when the two worlds seem so similar in makeup. Beneath that thin outer air, things change. The pressure grows. The temperature climbs in strange, uneven ways. And the gases give way to something the textbooks call ice, though it is not ice as you and I know it. This deep layer is a hot, dense, slushy mixture of water, ammonia, and methane, squeezed so hard that it behaves more like a thick fluid than anything frozen. It is the reason Neptune is called an ice giant. The ice is not cold. The ice is heavy, hidden, and warm. Think for a moment about the water inside Neptune. Water is 2 hydrogen atoms holding 1 oxygen atom. The hydrogen came from the dawn of the universe. The oxygen, though, came later, much later, born in the hearts of dying stars. Massive stars lived fast, burned bright, and then collapsed, scattering oxygen into space like seed on the wind. That oxygen drifted for ages, joined with hydrogen, and became water. Some of that water settled into Earth's oceans. Some of it, perhaps the very same kind, ended up locked into the dark depths of Neptune. The ammonia is a story too. Ammonia is nitrogen bound to hydrogen, and nitrogen also comes from the lives and deaths of stars. The methane, with its single carbon, carries the same lineage. Carbon is forged in old stars, in the slow burning of helium into heavier things. Every carbon atom inside Neptune was once inside a star that has long since gone quiet. The planet, in a sense, is a museum of stellar history, pressed into a sphere 4 times the width of Earth. Deeper still, scientists believe there is a small rocky and metallic core, perhaps about the size of Earth itself. Iron, silicon, magnesium, and other heavy elements may have settled there over billions of years. These are the same elements that make up the ground beneath your feet. The iron in your own blood, the calcium in your bones, the oxygen in your every breath. All of it traces back to the same long story of stars living and dying. Neptune simply gathered its share in a different shape. What remains uncertain is how these layers truly blend. Does the icy mantle have a clear boundary, or does it slowly fade into the gassy air above and the rocky core below? Some models suggest sharp layers, like a planet cut into clean shells. Other models suggest a soft, muddled interior with no clean lines anywhere. The truth is, we have never been deep enough to see. We have only flown past once, decades ago, and looked from the outside. Even Neptune's blue color, that gentle giveaway, may hide more than methane alone. One idea is that an unknown haze, made of particles we cannot yet name, deepens the shade. Another is that small differences in cloud thickness account for it. The question is open. The chemistry is partly written and partly blank. So as you drift, picture that quiet blue world made of starlight's old leftovers, holding water older than the sun, methane shaped by ancient carbon, and a heart we have never touched. Beneath the soft blue and green clouds of Uranus and Neptune, something strange is happening. We cannot see it. We have never touched it. But the forces working down there are some of the most extreme in the entire solar family. Start with gravity. Both planets are huge compared to Earth, though small compared to Jupiter and Saturn. Their gravity pulls inward with quiet, endless patience. Every atom of gas, every drop of liquid, every grain of ice is squeezed toward the center. The deeper you go, the harder the squeeze becomes. And the harder the squeeze, the hotter and stranger the material gets. Near the cloud tops, things feel almost gentle. The air is cold. The pressure is light. But drop down only a few hundred miles, and the weight of all that gas above begins to crush everything below. Hydrogen and helium thicken into a heavy fog. Water, ammonia, and methane mix together into a thick, dark soup. Scientists often call this layer the mantle, though it is nothing like the rocky mantle of Earth. It is hot. It is dense. And it may behave in ways no liquid on our world ever could. One leading idea is that this deep middle layer is a kind of warm, slushy ocean. Not water as you and I would know it. The pressure is so high that water molecules cannot stay in their normal form. They lose electrons. They flow like a strange electric fluid. Some researchers call it a supersonic state, a phase of matter that only forms under crushing conditions. We have made tiny flashes of it in labs on Earth for a fraction of a second. But inside an ice giant, this odd material may stretch for thousands of miles in every direction. This hidden ocean, if it exists, would also be where the magnetic field is born. On Earth, our magnetic field comes from molten iron deep in the core. On Uranus and Neptune, the field may come from this strange churning fluid much closer to the surface. That could explain why their magnetic fields are so tilted and so lopsided. But the truth is, we are still guessing. We have only flown past these worlds once, decades ago, and the readings raised more questions than they answered. Heat is another quiet force at work. Neptune, in particular, glows with its own warmth. It gives off more energy than it receives from the distant sun. Something inside is still cooling, still releasing leftover heat from its birth long ago. Or perhaps something is still settling, still falling toward the center, releasing energy as it sinks. Uranus, for reasons no one fully understands, gives off almost no extra heat at all. Two worlds, built from similar stuff, behaving in completely different ways. The reason remains one of the great open puzzles of planetary science. Pressure shapes everything. At the cloud tops, the pressure is similar to what you might feel standing on a high mountain. A few hundred miles down, it grows to thousands of times the pressure at Earth's surface. Deeper still, it climbs to millions of times. Atoms cannot keep their normal shapes. Molecules break apart and reform into new arrangements. The simple rules of chemistry that we learn on a calm afternoon begin to bend. Down there, matter has to invent new ways to exist. Then there is the slow pull of time. These forces have been at work for more than 4 billion years. Every second of that long history, gravity has been squeezing. Heat has been leaking outward, and the strange interior fluids have been stirring. Tiny currents, given enough time, can build vast patterns. The magnetic fields may flip and tilt because of these slow movements. The cloud bands at the surface may be the faint echo of much larger flows hidden far below. We rarely think of tidal forces with the ice giants because their moons are small and their distances are great. But even here, gentle tides matter. Triton, Neptune's largest moon, pulls on the planet as it orbits in the wrong direction. Over long ages, that pull steals a little energy. The same kind of tidal whisper shapes the orbits of Uranus's many moons, slowly nudging them into the patterns we see today. What lies beneath those soft clouds is, in the end, mostly a mystery. We have models. We have computer simulations. We have a single brief flyby from a small spacecraft long ago. We do not have a true map of the interior. We do not know exactly where the gas ends and the slush begins. We do not know if there is a solid core or only a gradual thickening into something even stranger. The forces are real. The picture is still soft, still waiting to come into focus. Somewhere far below the soft blue cloud tops of Uranus and Neptune, the pressure begins to climb. It climbs slowly at first, then steeply, then to numbers that are hard to picture. Near the centers of these two worlds, the pressure may reach several million times the pressure you feel right now, sitting still in your room. To put that in gentler terms, imagine stacking the weight of a small mountain onto the tip of your finger. Then imagine stacking 1,000 more mountains on top of that. That is the kind of squeeze we are talking about. The temperatures down there are just as hard to hold in the mind. The outer clouds of Neptune are bitterly cold, around minus 200 degrees Celsius, cold enough that the air itself would freeze on your skin. But as you fall inward, the world warms quickly. A few thousand kilometers down, the temperature may rise to thousands of degrees. Hot enough to melt iron, hot enough to glow. And yet the material at that depth does not behave like anything you have ever touched. This is where one of the strangest ideas in planetary science begins. Some researchers wonder if, deep inside these two worlds, it actually rains diamonds. Not little flecks, not dust, real, solid diamonds drifting slowly downward through a hot, dense sea. The idea sounds like a fairy tale, but it comes from real chemistry. Uranus and Neptune are rich in methane, a simple molecule made of one carbon atom bonded to 4 hydrogen atoms. Methane gives Neptune much of its deep blue color. Under the gentle conditions of the upper atmosphere, methane behaves like an ordinary gas. But push it down into the crushing pressures of the mantle, heat it to thousands of degrees, and the bonds begin to break. The hydrogen drifts one way. The carbon clings to itself. And carbon, when squeezed hard enough and heated just right, can rearrange into the tight, sparkling lattice we know as diamond. In laboratories on Earth, scientists have actually watched this happen. They take a thin film of plastic, which is also rich in carbon and hydrogen, and they blast it with a powerful laser to mimic the conditions deep inside an ice giant. For a tiny fraction of a second, the sample reaches those impossible pressures and temperatures. And inside that flash, tiny diamonds appear. The experiment has been repeated, and each time the result is the same. Diamond formation under ice giant conditions is not a fantasy. It is something that nature seems perfectly willing to do. What we do not know is how big the diamonds get. Some researchers picture them as fine grains, almost like sand drifting through the deep. Others imagine them growing slowly, layer by layer, into stones the size of marbles. A few have suggested they might, given enough time, grow to the size of fists, or even larger before sinking down toward the rocky core. No one can say for sure, because no probe has ever come close to seeing it. Everything we believe about the inside of Uranus and Neptune comes from models, from gravity measurements, and from a single flyby long ago. If the diamonds are real, picture the scene. A warm, dense ocean of hot, slushy ice and broken molecules, stretching for thousands of kilometers in every direction. No light, no sound that would carry to your ears, just heavy, slow currents moving in the dark. And falling through that ocean, slowly, patiently, tiny crystals catching nothing, because there is nothing to catch, sinking toward a core we have never seen. To grasp the scale of where this would happen, try a small comparison. If you shrank Neptune down to the size of a basketball held in your hands, the layer where where diamonds might form would still be deeper than the thickness of the rubber skin. The whole region would be larger than the Earth, and the pressure inside that region on our shrunken basketball would still be enough to crush any tool we have ever built. There is no guarantee that the diamond rain is real. It might be a phenomenon limited to narrow zones we have not yet mapped. It might be more common than we suspect, falling steadily across millions of cubic kilometers. The chemistry suggests it is possible. The experiments suggest it is possible. But the truth, the actual seeing of it, remains beyond reach. So tonight, as you settle in, let your mind drift gently downward through those soft blue clouds, past the cold, past the dark, into a hidden sea where perhaps something is quietly falling and has been falling for billions of years. Imagine drifting high above the cloud tops of Uranus, suspended in a thin veil of pale blue-green haze. The light here is soft, filtered, almost dreamlike. The sun is a small bright point, no larger than a distant street lamp, casting weak shadows across endless cloud decks. Below you, the atmosphere fades into deeper shades of cyan and teal, smooth and featureless, like a calm sea with no shore. And all around you, invisible but powerful, something strange is happening. The magnetic field of this world is wrapping around you in ways that should not make sense. On Earth, a compass points roughly north. The magnetic field flows in a tidy pattern, like iron filings around a bar magnet placed near the planet's center. The poles sit close to the spin axis. The geometry is neat. The same is true for Jupiter and Saturn. But at Uranus, the rules seem to fall apart. The magnetic field is tilted nearly 60 degrees from the spin axis. Worse still, the magnetic center is not at the heart of the planet at all. It sits offset, pushed toward one side, as if someone took a magnet and shoved it deep into one hemisphere and left it there. If you could see the magnetic field with your eyes, the view would be dizzying. Lines of force would loop outward in lopsided arcs, twisting and snapping in strange directions. As Uranus turned beneath you, the field would tumble like a child's toy thrown into the air. Each rotation would sweep the field through wild new shapes. The world would not so much spin under a steady magnetic crown as wobble inside a tangled cage of invisible threads. Neptune is no better. From a perch above its deep blue cloud tops, you would see a world that looks more orderly than Uranus on the outside. The bands of cloud are sharper. The winds are fiercer. The color is a rich indigo, like ink mixed with light. And yet the magnetic field around Neptune is just as confused. Its axis tilts about 47 degrees from the spin axis, and its center is also offset from the planet's middle. Two worlds, side by side in the outer solar system, both breaking the gentle pattern set by every other planet we know. This is one of the quiet mysteries the ice giants keep. We do not know why their magnetic fields behave this way. We have theories, and each one paints a different picture of what may lie inside. One idea is that the field is generated not in the deep core, as it is on Earth, but in a shallower layer closer to the surface. Beneath the visible clouds, both planets are thought to hold a vast region of hot, slushy fluid. This fluid is sometimes called a mantle of ices, though it is nothing like the ice in a freezer. It is a thick, electrically charged ocean of water, ammonia, and methane, squeezed under enormous pressure. If the magnetic field is born in a thin shell of this fluid, instead of in a deep central dynamo, the geometry could come out tilted and lopsided, just as we see. Another idea is that the inside of each planet is not arranged in neat layers at all. Instead, the interior may be patchy, with regions of different density swirling slowly past each other. A patchy interior could stir the electric currents in messy ways, twisting the field into the strange shapes the spacecraft measured. We do not yet know which picture is closer to the truth. We have only a single set of measurements from Voyager 2, taken during brief flybys decades ago. From your imagined perch above the clouds, none of this would be visible. The atmosphere would look calm. The light would stay soft, but somewhere below your feet, deep beneath the haze, something is generating one of the most unusual magnetic environments in the solar system. Charged particles from the sun, caught in this tangled field, would be flung along strange paths. Auroras, where they exist, would not glow politely at the poles. would flicker in odd places, far from where you might expect, painting faint patches of light into the night side of each world. Sit with that picture for a moment. Two pale, distant planets, wrapped in invisible fields that tumble and lean in ways we still cannot fully explain. The clouds drift in silence above an interior we have never touched. The field lines twist outward into space, carrying their secret with them. And somewhere, in the slow churn of fluids we have never seen, the answer is waiting. For now, it remains one of the gentler puzzles of the outer dark. Saturn wears its rings like a wide, bright skirt of ice, easy to see through even a small telescope from a backyard on Earth. Uranus wears something far quieter. Its rings are thin, dark, and shy. For most of human history, no one even knew they were there. They wait in the cold, almost invisible, reflecting only a tiny sliver of the faint sunlight that reaches them. To find them at all, you have to look very carefully, and even then, they slip past the eye like dark thread on dark cloth. The rings of Uranus were not seen directly when they were first discovered. In 1977, astronomers were watching a distant star pass behind the planet. They expected the star to fade smoothly, blocked by the body of Uranus. Instead, the star blinked. It dimmed, brightened, dimmed again, in a pattern that did not match the planet alone. Something thin and narrow was passing in front of it. Something nobody had charted before. The blinks gave away a set of slim rings, dark as soot, circling a world no probe had yet visited. When Voyager 2 finally swept past Uranus in 1986, it confirmed what those star blinks had suggested. The planet was wrapped in narrow, dusky bands of material. There were 9 main rings then, with a few more added later from closer study and from the Hubble Space Telescope. The total now sits at 13 known rings, give or take, depending on how you count the faint outer ones. Some are tightly packed and sharp-edged. Others are broad and dim, more like haze than ribbon. What makes the rings so dark is one of the gentle puzzles of the outer solar system. The bright ice in Saturn's rings reflects sunlight like fresh snow. The rings of Uranus reflect almost nothing. they are as black as coal dust, or perhaps darker still. One idea is that the ring particles are covered in a kind of carbon-rich grime, slowly cooked by radiation and time. Another possibility is that the rings contain methane ice that has darkened over long ages, baked into a sooty crust. No one has yet brought a sample home to check. The dark color remains a quiet, open question. The shapes of the rings raise their own gentle puzzles. Some of the rings are not round at all. The epsilon ring, the brightest of them, is shaped a little like a stretched oval, wider on one side than the other. Its edges are unusually sharp, as if something is holding the particles in place. Two small moons, Cordelia and Ophelia, orbit just inside and just outside this ring. Many researchers think these tiny moons act as shepherds, their gravity nudging stray particles back into line. But the other narrow rings do not all have such clear shepherds. What holds them so tight is not fully understood. The particles themselves are not the fine dust of Saturn's rings. Many of the chunks circling Uranus seem to be larger, closer to the size of pebbles, cobbles, even boulders. Between the main rings lie broader sheets of finer dust, only seen clearly when Voyager looked back at the planet from the far side, with the sun shining through. From that angle, the dust lit up, revealing structures the inbound view had missed. It was a reminder that the rings of Uranus look different depending on where you stand. Where did all this material come from? That, too, remains uncertain. One thought is that the rings are the shattered remains of small moons, broken apart long ago by impacts or by tidal stress. Another idea is that they formed alongside the planet itself, leftover bits that never managed to gather into a moon. The rings may be young, only a few 100 million years old, or they may be ancient. Without samples or a closer look, the timeline stays open. Because Uranus is tipped on its side, the rings tilt with it. They do not lie flat around the sun the way Saturn's do. Instead, they circle the planet's equator, which itself rolls almost perpendicular to the planet's path. From our distant view, the rings sometimes appear edge-on, almost vanishing into a thin line. At other times, they open up into a full circle, like the iris of a slow, watching eye. The cycle takes decades, matching the long seasons of the planet. There is something restful about these dark, quiet rings. They are not flashy. They do not catch the light or call attention to themselves. They simply turn slowly in the cold, keeping their secrets close. What they are made of, how they formed, why some hold their shape so neatly. These are questions still waiting in the dark, patient as the rings themselves. Far out in the dim blue light around Neptune, there are rings. Not the bright, broad bands that circle Saturn. Not even the soft, dark rings of Uranus. Neptune's rings are something stranger, something fainter, something that seems to come and go in slow, quiet rhythms we still do not fully understand. For a long time, no one knew Neptune had rings at all. Astronomers searched for them in the 1980s by watching the planet pass in front of distant stars. When a ring is present, the starlight should dim for a brief moment as the dust blocks it. Sometimes the light dimmed. Sometimes it did not. The results were odd. The rings seemed to be partial, broken, like beads strung loosely on an invisible thread. When Voyager 2 finally swept past Neptune in 1989, it saw what the ground-based telescopes had been hinting at. Neptune does have full rings, faint and dark, made of dust as fine as smoke. But within one of those rings, called the Adam's ring, the dust is not spread evenly. It clumps. It gathers into bright arcs, glowing patches of material separated by long stretches of near emptiness. The arcs were given quiet names like liberté, égalité, fraternité, and courage. Here is where the cycles come in. Rings should not behave this way. The laws of motion, as we understand them, want to smooth the dust out. A clump of particles orbiting Neptune should slowly spread along its path, like a drop of cream stirred into dark coffee. After a few decades, the arcs should blur into one continuous, faint ribbon, and yet for a long time they did not. They held their shape. They orbited Neptune as bright knots, year after year, refusing to dissolve. One idea is that a small moon, hidden nearby, gently herds the dust into place. Its gravity could act like an invisible shepherd, nudging stray grains back into the arc whenever they drift. The moon Galatea, which orbits just inside the atom's ring, is the leading suspect. Its tugs may set up a slow resonance, a repeating pattern in which the dust is squeezed into certain pockets and emptied from others. In this view, the arcs are not random. They are the visible song of a quiet gravitational rhythm playing out over and over. But the question is far from closed. When astronomers look at Neptune's arcs today, using powerful telescopes on Earth, the arcs no longer look the way they did in 1989. Some have faded. Courage, once a small but distinct knot, appears to have shifted along the ring before growing very faint. Liberté, too, seems to be slowly dimming. Fraternité and égalité remain, but they may not stay forever. The pattern is changing on a timescale of human lifetimes. So the cycle here is strange. The arcs are stable enough to last decades, yet not stable enough to last centuries. They pulse and weaken and shift, as if responding to forces we have not yet identified. Some researchers wonder if tiny unseen moonlets are being slowly ground down by collisions, feeding new dust into the rings, while older dust drains away. Others suggest that Galatea's gentle herding is simply not strong enough to hold all the arcs in place, and that we are watching a slow decay. The rings of Neptune fading on a clock we cannot yet read. There is also the question of how the rings formed at all. One possibility is that a small moon was shattered long ago, perhaps by a passing comet, and the rings are the lingering dust of that ancient breaking. Another possibility is that the rings are constantly renewed by tiny moons quietly chipping away at one another. We do not know which story is true. We may not know for a long time. What we do know is this: around a planet so far from the sun that its sky is a deep cobalt twilight, dark threads of dust trace slow circles. Within those threads, brighter clumps drift like soft glowing beads, separated by long velvet gaps. They turn around Neptune in a rhythm of hours and days and decades. And somewhere within that rhythm, the arcs are slowly changing, brightening here, fading there, shifting their places along the ring. It is a quiet cycle, a breathing almost, a pattern that pulses across timescales longer than a human life, but shorter than than the age of the planet itself. The next telescope to look closely may find the arcs further dimmed, or it may find new ones, forming where none were seen before. For now, the faint rings of Neptune keep their slow secret, turning in the cold dark, asking us to wonder how long they will last. Of all the moons that orbit Uranus, one stands apart in a way that still puzzles those who study it. Its name is Miranda, and it is small, only about 470 kilometers across. You could fit it inside many countries on Earth, and yet, for its modest size, it carries some of the strangest scenery in the entire solar family. When Voyager 2 passed by Miranda in 1986, the images it sent back surprised nearly everyone. The little moon looked stitched together, as if pieces of different worlds had been gathered and pressed into one. There were smooth plains beside jagged ridges. There were curved grooves, like the patterns left in soft clay. And there were cliffs, towering, pale cliffs of ice that seemed to fall away into shadow. One of those cliffs is called Verona Rupes. It may be the tallest known cliff in the solar system. Its height is uncertain, but estimates place it somewhere around 20 kilometers from top to bottom. That is more than 10 times the depth of the deepest canyon on Earth. If you stood at its edge in Miranda's weak gravity and stepped off, you would fall for many minutes before reaching the bottom. The drop would feel slow, dreamlike, almost gentle. What made these cliffs is one of Miranda's quiet, open questions. The surface tells a story that no one has yet fully read. Some researchers wonder if Miranda was once shattered by a great impact, then slowly pulled back together by its own gravity, the pieces settling unevenly into the strange patchwork we see today. Others suggest a different idea. They propose that warm ice from deep inside the moon rose toward the surface in slow, churning blobs, reshaping the crust from below. In that case, no shattering was needed. The moon simply rearranged itself from within. Both theories have weaknesses. The shattering idea struggles to explain why the patchwork looks so neatly arranged in places. The internal churning idea struggles to explain how such a small moon could hold enough warmth to drive that kind of motion. Miranda is tiny, and small bodies cool quickly. Something must have heated it long enough to soften its ice, and the source of that heat remains uncertain. Perhaps gravity from Uranus, and the other moons once tugged on Miranda in ways that warmed its insides. That tugging may have faded long ago, leaving the frozen evidence behind. Miranda does not travel alone. It is part of a quiet family of moons that circle Uranus in slow, patient orbits. There is Ariel, with its bright, grooved surface. There is Umbriel, dark and ancient, and covered in craters. There is Titania, the largest, marked by long canyons that hint at ice once flowing across its face. And there is Oberon, scarred and old, sitting farthest out among the major five. These moons drift together in a kind of slow dance, each one shaped by its neighbors, each one tugging gently on the others as they orbit. That gentle pulling matters more than it sounds. Over long stretches of time, the small gravitational nudges between moons can shift their orbits, stretch them, warm their interiors. Some researchers wonder if Miranda once passed through a special arrangement with another moon, a kind of resonance where their orbits matched in simple rhythms. Such a rhythm could have flexed Miranda's ice, heated it from within, and driven the strange motions that built those cliffs and grooves. If that idea is right, Miranda's surface is a record of a vanished alignment, a moment in the deep past when the moons of Uranus moved in step, but the evidence is incomplete. Voyager 2 saw only one side of Miranda clearly. The other side has never been mapped in detail. Whatever secrets it holds, whatever cliffs or plains or unexplained ridges remain hidden in the darkness on the far side of the moon. No spacecraft has returned. No closer look has been possible in nearly 4 decades. So Miranda continues on its quiet path, circling its tilted planet in the cold outer reaches of the solar system. Its cliffs catch the faint sunlight glowing pale against the black. Its grooves trace patterns no one has yet decoded. Somewhere beneath its frozen crust, the answer to its strange face may be locked away, waiting. The little moon turns, slow and silent, around a world that itself lies on its side, and we, watching from far away, can only wonder what shaped it, and whether the family of moons that surrounds it once moved in some forgotten harmony we no longer see. The question stays open, soft and unhurried, like the moon itself. Uranus carries with it a small family of moons, and they are among the coldest places we have ever seen. 27 of them have been counted so far, though more may still wait in the dark. They are named not for old gods, as most moons are, but for characters from old plays and poems. Titania, Oberon, Umbriel, Ariel, Miranda, and a long list of smaller ones drift in slow circles around the tilted planet. Each one is its own frozen world, and each one holds questions we have not been able to answer. The temperatures out there sit near -200 degrees Celsius. That is so cold that water ice behaves like solid rock. If you stood on one of these moons and struck the ground with a hammer, the ice would not chip like a snowball. It would shatter like stone. The whole surface is locked in a deep, ancient stillness, with no liquid water, no flowing air, and almost no warmth from the distant sun. Titania is the largest of the family. It stretches about 1,500 kilometers across, which is roughly the width of a small country folded into a sphere. Its surface is a soft gray, marked by long canyons and faint craters. Some of those canyons run for hundreds of kilometers, like cracks in a frozen pond that never thawed. One possibility is that Titania once had a warmer interior, and as it cooled, the outer shell pulled apart and split. Whether any of that warmth still lingers deep inside is a question we cannot yet answer. Oberon, just slightly smaller, looks older and more battered. Its surface holds dark patches at the bottoms of some craters, as though something rose from below and settled there long ago. Some researchers wonder if this dark material is a kind of ancient slush, a mix of ice and carbon-rich chemistry that seeped up through cracks. Others think it may simply be dust gathered over billions of years. The truth is still hidden under the frozen crust. Umbriel is the darkest of the larger moons. It reflects very little light, almost as if it were dusted in soot. At its north pole sits a bright ring called Wanda, a strange circle that stands out against the gloom. no one is certain what made it. One idea is that Wanda is a young impact crater whose floor is filled with cleaner ice. Another is that some chemistry beneath the surface created a patch of frost in just that spot. Voyager 2 only saw it from one angle, and we have not been back since. Ariel, by contrast, is the brightest of the Uranian moons. Its surface looks younger, smoother, with long valleys that suggest some kind of slow flow in the distant past. Whether that flow was warm ice acting like soft taffy, or something stranger like ammonia-rich slush, no one can say for certain. The question of how Ariel kept itself active for so long, so far from the sun, remains open. The most extreme of them all may be the smallest of the major five. Miranda is only about 470 kilometers wide, smaller than many countries, yet it holds some of the tallest known cliffs in the solar system. The cliff called Verona Rupes drops perhaps 20 kilometers straight down. If you stepped off the edge in Miranda's weak gravity, you would fall for nearly 12 minutes before reaching the bottom. 12 quiet minutes of slow, silent drifting through the cold. Then there are the smaller moons, the inner shepherds that move among the rings. Some of them are so close together that researchers wonder how they have not crashed into one another long ago. A few may be slowly drifting toward collisions over millions of years. If that is true, then the inner system of Uranus is changing very slowly, in ways we have only begun to notice, far out beyond the main family. A swarm of tiny, irregular moons traces wide, tilted loops around the planet. Many of them travel backward compared to the rest. They are likely captured objects, drawn in from elsewhere by Uranus long ago. Their origins, their compositions, their true number, all remain uncertain. What ties these worlds together is silence. They do not glow with auroras we can easily see. They do not sing with radio storms. They simply turn slowly in the deep cold, each one a frozen record of something that happened long before any of us were here. The question of what hides beneath their crusts, and whether any of them still hold a flicker of warmth, is one we may not answer in our lifetimes. For tonight, it is enough to picture them, pale and patient, in the long shadow of their tilted world. Of all the moons that drift around the ice giants, one stands apart in a way that still puzzles the people who study it. Its name is Triton, and it belongs to Neptune. It is the largest of Neptune's moons by far, a frozen sphere about 1,700 miles across, wrapped in a pale pink and white crust of nitrogen ice. From a distance, it looks almost like a soft pearl, faintly blushed, glowing in the dim sunlight that reaches that far edge of our solar family. What makes Triton strange is the way it moves. Nearly every large moon in the solar system circles its planet in the same direction the planet spins. Triton does the opposite. It travels backward around Neptune in what scientists call a retrograde orbit. No other large moon does this, and that single quiet detail has shaped almost everything we believe about where Triton came from. The leading idea is that Triton did not form near Neptune at all. It may have been born much farther out, in the cold belt of small icy worlds beyond the orbit of Pluto. That region is called the Kuiper Belt, and it is full of frozen bodies left over from the early solar system. Long ago, the thinking goes, Triton may have wandered too close to Neptune and been pulled in, captured by gravity like a stone caught in a slow whirlpool. If that is true, Triton is not really Neptune's child. It is an adopted world. Other ideas exist. Some researchers wonder whether Triton was once part of a pair, a binary, two icy bodies orbiting each other as they drifted through space. When the pair passed near Neptune, one was flung away and the other was kept. That would explain how Neptune managed to catch something so large without simply tearing it apart. But the details remain open. We do not yet know exactly how the capture happened, only that the math suggests it must have somehow. If you slow down and look at Triton's surface, you find textures that almost no one ever talks about. Much of it is covered in a strange pattern that scientists have nicknamed cantaloupe terrain, because it looks faintly like the dimpled skin of a melon. Soft, rounded pits sit close together, separated by gentle ridges. Nothing else in the solar system looks quite like it. The pits are roughly the same size, around 20 miles across, and they spread across vast regions of the moon. How they formed is still an open question. One possibility is that slow-moving ice rose from below in soft blobs, pushing the surface upward and then settling again. Another is that the crust slowly collapsed in places where warmer material drained away beneath it. The truth may be a mix of both, or something we have not yet thought of. Triton's surface is one of the coldest places ever measured in the solar system. The temperature there hovers near minus 390 degrees Fahrenheit. At that chill, nitrogen freezes into a thin, solid layer, and methane and carbon monoxide turn into frost. The light that falls on this frost is faint, only a tiny fraction of what reaches Earth. Yet, that pale light is enough to gently warm the ice, and the ice responds in slow, subtle ways. There is a thin atmosphere too, mostly nitrogen, so thin it would feel like vacuum to us. But it carries faint winds, and those winds leave streaks across the surface. Voyager 2, the only spacecraft ever to visit, photographed long dark trails laid across the southern hemisphere. They look like brush strokes painted with a careful hand. Most researchers think these streaks come from material lifted into the sky by some quiet process below the surface, then carried sideways by the breeze before settling back down. The shape of Triton's orbit adds another layer to the mystery. The orbit is almost perfectly circular, which is unusual for a captured body. A newly caught moon should have a stretched, lopsided path. Something must have smoothed Triton's orbit over time. Perhaps the slow tug of tides squeezing and releasing the moon for hundreds of millions of years. That squeezing would have heated the inside of Triton, and that heat may still linger deep beneath the ice, which raises the gentlest question of all. If Triton was once warmed enough by tides, and if some of that warmth remains, could there be liquid water hidden far below its frozen shell? No one knows for sure. The evidence is incomplete, and we have not been back since Voyager passed by in 1989. For now, Triton waits in the dark, turning the wrong way, holding its small secrets close. In the long, quiet history of how we learned about the outer worlds, few moments feel as strange and unexpected as the day we discovered that a frozen moon could spit. Triton, the largest moon of Neptune, was thought to be one of the deadest places in the solar system. Its surface sits at around minus 235 degrees Celsius, colder than almost any other body we had ever measured. A world that cold should be still. It should be sleeping under its ice, locked in place for billions of years. And yet, when our one and only visitor arrived in the summer of 1989, it found something no one had predicted. That visitor was Voyager 2, a small spacecraft about the size of a compact car, carrying cameras, sensors, and a golden record meant for any mind that might one day find it. Voyager 2 had already passed Jupiter, Saturn, and Uranus. By the time it reached Neptune, it had been traveling for 12 years. Its cameras were old by then. Its computer was slower than the phone in your pocket. The signal it sent home was so faint that engineers had to link giant radio dishes across the earth just to hear it whisper. When Voyager 2 swung past Neptune and looked down at Triton, the team back on Earth expected a cratered, frozen ball. They expected an old surface, scarred and unchanging, like the highlands of our own moon. What they saw instead was something closer to a sculpture. The surface had odd ridges and dimples that looked a bit like the skin of a melon. There were smooth plains where craters should have been. Something had reshaped this moon, and not so long ago. The bigger surprise came when scientists studied the images more closely. Across the southern polar cap, they spotted dark streaks, long, thin smudges that all pointed roughly the same direction, like soot smeared across a pale tablecloth. At first, no one was sure what they were. Then, after careful study, two of the images revealed something almost impossible to believe. Plumes, tall, narrow columns of dark material rising from the surface, climbing perhaps 8 kilometers into the thin sky, then drifting sideways in a high, slow wind. Triton had geysers, active ones, on a moon so cold that nitrogen freezes solid on the ground. The discovery sent the science team into long, careful debate. How could a world this frozen still be doing anything at all? One leading idea is that sunlight, even the faint sunlight reaching Neptune, warms the underside of a thin, clear nitrogen ice layer at the surface. The warmth builds up like heat, nitrogen gas pressure grows beneath the ice until it finds a weak point and bursts upward, carrying dark dust with it. This is sometimes called the solid greenhouse model. It is elegant. It fits some of the evidence, but it is not the only possibility. Another idea suggests that the heat comes from inside Triton itself. Perhaps slow tides from Neptune squeeze the moon gently, warming its interior. Perhaps radioactive elements deep within still glow with a tiny, steady heat. If so, the geysers might be fed from below, not from the sun above. Researchers still cannot say for certain which picture is correct. Both could be partly true. The plumes Voyager saw were so brief, so distant, and so few that the data has been studied and restudied for decades without a clean answer. What we do know is that Triton broke a quiet assumption we had carried for a long time. We had thought activity required warmth, and warmth required closeness to the sun. Triton suggested otherwise. A world far past the orbit of Neptune, drifting in near total darkness, could still have something stirring at its surface. That single realization rippled outward. It changed how scientists thought about Pluto, about distant icy bodies, about moons orbiting giant planets in other star systems. Voyager 2 spent only a few hours close to Triton before continuing on into the deep. It has never returned. No spacecraft has visited since. Every image we have of those geysers, every measurement of that strange pink and gray surface comes from that one brief flyby more than 30 years ago. Everything we think we know about the geysers of Triton rests on a handful of photographs taken by an aging machine moving past at thousands of kilometers per hour. The mystery has been waiting patiently ever since. Somewhere out there, in the long shadow of Neptune, dark plumes may still be rising into a pale sky, or they may have gone quiet. We have no way to check. For now, we sit with the question and we wonder. There is something quietly strange about the ice giants that few people expect. They are the coldest planets in our solar system, sitting far from the warmth of the sun. And yet, they hold the fastest winds we have ever measured anywhere among the planets. On Neptune, ribbons of cloud race around the world at speeds that would shatter anything built on Earth. Some of these winds blow faster than the speed of sound in our own air. It seems almost backwards. The further you travel from the sun, the less energy reaches a planet, and the calmer you might expect its weather to be. Yet Neptune does the opposite. The colder it gets out there, the wilder the sky becomes. When Voyager 2 swept past Neptune in 1989, the cameras caught long white streaks of cloud being pulled across the deep blue face of the planet. Scientists timed how quickly those clouds moved. The numbers came back so high that the team checked them again, just to be sure. Some winds reached around 1,500 kilometers per hour. That is faster than a passenger jet at full power, faster than the swiftest storms on Jupiter, which is a far larger and far more energetic world. Neptune, so distant and so dim, somehow stirs the strongest gales in the known planetary family. This is one of the quiet puzzles that still sits unsolved. A planet's weather usually draws its energy from sunlight. The sun heats the air rises, and the spinning of the world bends those rising currents into winds. But Neptune receives only a faint trickle of sunlight. The sun from out there looks like a very bright star rather than a glowing disk. There is barely enough warmth in those upper clouds to drive a gentle breeze, let alone supersonic jets. And still, the winds tear across the sky. One idea is that Neptune's weather is powered from below rather than from above. The planet gives off more heat than it receives from the sun. Deep inside, something is still warm, still glowing softly, still pushing energy outward. That inner heat may rise through the layers of the atmosphere and feed the great wind bands at the top. In this picture, Neptune is like a kettle that has been left on a very low flame for billions of years. The sun barely matters. The real engine is buried far below the clouds. Another idea points to the thinness of the upper atmosphere itself. With less material to push around, even small amounts of energy can move the gas to very high speeds. Some researchers wonder whether the winds we see are only a shallow skin, racing across a much slower, calmer interior. If that is true, the supersonic streaks may be more like the surface of a fast-flowing river, with quieter water beneath. Other models suggest the winds reach much deeper, perhaps thousands of kilometers down into the planet. We do not yet know which picture is closer to the truth. Uranus shows its own version of the puzzle. Its winds are slower than Neptune's, but still strong, with gusts measured at around 900 kilometers per hour in some bands. What is strange is that Uranus appears to give off almost no extra inner heat. By the logic that works for Neptune, Uranus should be a quieter, calmer world, and in some ways it is. Yet it still manages powerful jet streams that flow in opposite directions at different latitudes. Something is driving them, and we are not sure what. There is also the question of why the winds blow the way they do. On both ice giants, the air near the equator drifts backward against the spin of the planet. Further toward the poles, the winds turn around and race forward with the spin. Earth has nothing quite like this pattern. Jupiter and Saturn have many narrow bands of alternating winds, but Uranus and Neptune seem to have only a few broad currents. Why these planets settled into such simple, fast, lopsided patterns is still being studied. It is a strange thing to picture as you rest. Out there in the cold and the dark, far beyond the asteroids and the gas giants, two pale blue worlds spin in near silence. Their cloud tops glow faintly under a distant sun. And across those clouds, winds louder than any storm on Earth race in long, quiet ribbons, driven by something we cannot quite name. No one hears them. No instrument sits among them. They blow and have blown for ages in a place where no human has ever been. The mystery of what powers them is still open, waiting in the dark. On a summer day in 1989, a small spacecraft slipped past Neptune and saw something that no one expected. A dark oval, wider than the Atlantic Ocean, drifted across the planet's deep blue face. Voyager 2 sent the picture home, and astronomers gave the feature a simple name. They called it the Great Dark Spot. It looked steady, almost permanent, like a bruise in the clouds that might last for centuries. But Neptune had other plans. When the Hubble Space Telescope turned its eye on the planet a few years later, the spot was gone. No fading edges, no slow drift toward the pole. Just an empty stretch of blue where a continent-sized storm had been. In the years since, new dark spots have appeared, swirled for a while, and then dissolved again. The planet seems to grow them and erase them on its own slow schedule, and no one is entirely sure why. These spots are not like the famous storm on Jupiter, which has churned in the same place for centuries. Neptune's spots are softer, shorter-lived, and stranger. They drift through the atmosphere like dark moods, passing across a face. Some last for a few years. Others vanish within months. They tend to form at middle latitudes, then wander toward the equator, and somewhere along the way, they simply stop being there. To understand them, it helps to think of the planet as a system rather than a single object. Neptune does not exist alone. It hangs in the faint light of a distant sun, bathed in solar wind, tugged by its own deep heat, and shaped by the slow churning of fluids far beneath the visible clouds. Each of these forces plays a part in the weather we see, and the dark spots may be where all those forces briefly meet. One idea is that the spots are high-pressure vortexes, spinning columns of gas that push the upper haze aside and let us peer into deeper, darker layers. In this view, the spot itself is not really dark. It is a window. Below the bright methane haze, the atmosphere is shadowy and clear, and a vortex simply parts the curtain for a while. When the vortex weakens, the haze drifts back, and the window closes. Another idea points to the inner heat of Neptune. The planet glows with more energy than it receives from the sun, leftover warmth from its long-ago formation. That warmth rises from the deep interior in slow, uneven plumes. Where a plume reaches the cloud tops, it may stir the air into great rotating systems. If the plumes shift or fade, so do the spots above them. The connection between the deep heat and the visible weather remains one of the most interesting open puzzles about this world. There may also be a link to the distant sun. Even at 3 billion kilometers away, sunlight still touches Neptune's clouds and warms the upper haze. Tiny changes in that warming, spread over long seasons, may help decide when a spot can form and how long it can hold its shape. Some researchers wonder if the 11-year cycle of solar activity leaves a faint fingerprint on Neptune's weather. The data is thin, and the question stays open. What makes these spots feel like a symphony is how many instruments seem to play together to make them. The slow rotation of the planet, the inner heat rising from below, the methane haze drifting above, the faint pull of sunlight, the chemistry of clouds freezing and thawing at different depths. Each one alone would not be enough. Together, they may shape a storm large enough to swallow our planet whole, and then, just as quietly, let it go. The same kind of question echoes outward to other worlds. Jupiter's great red spot is shrinking, and no one is sure why. Saturn sometimes grows enormous white storms that wrap around the planet, then sleeps for decades. Uranus, Neptune's pale cousin, shows its own faint dark spots from time to time, though they are harder to catch. Each gas world seems to keep its weather in its own private rhythm, and we are still learning the music. For now, Neptune's dark spots come and go on a schedule we cannot predict. We watch them appear in fresh telescope images and feel a small thrill of recognition. We watch them fade and wonder where the storm energy went. The planet keeps its secret, drifting along its slow orbit, painting and erasing these dark ovals against the blue. Somewhere beneath the clouds, the deep heat keeps rising. Somewhere far above, the faint sunlight keeps falling. And between them, the weather of an ice giant keeps changing in ways we are only beginning to read. A year on Uranus lasts about 84 Earth years. A year on Neptune stretches even longer, close to 165. These vast orbits mean that the seasons on the ice giants do not pass in months. They pass in decades. A child born when summer begins at Neptune's south pole might grow old and gray before the season ever turns. This slow rhythm is hard for us to picture. On Earth, we feel the year as a steady cycle of warm and cool, light and dark. We watch leaves turn, snow fall, flowers open. The seasons mark the small chapters of our lives. On Uranus and Neptune, those same chapters last longer than most human lifetimes. A single season is the length of an entire career, or a marriage, or a quiet childhood remembered from a distant room. Uranus has the strangest seasons of any planet we know. Its axis is tipped almost completely on its side by about 98 degrees. Instead of spinning upright like a top, it rolls along its orbit like a ball. This means that for roughly 21 Earth years at a time, one pole stares straight at the sun, while the other sits in total darkness. The light at the pole never sets. The darkness at the other pole never lifts. Then, slowly, the angle shifts, and the long polar day begins to fade. We can only guess what this does to the weather below the clouds. When Voyager 2 flew past Uranus in 1986, the southern hemisphere was deep in its long summer, and the planet looked almost featureless. A smooth blue-green ball with very few visible storms. But as the years passed and the angle of sunlight shifted, telescopes on Earth began to see something change. Bands appeared. Bright clouds bubbled up. Storms swirled into view. The planet that once seemed quiet had begun to wake. Some researchers wonder if Uranus is most active during its equinox, when sunlight finally reaches its long-shadowed regions. The energy from that returning light may stir up the deep atmosphere, lifting warmer gas toward the cloud tops. Others suspect the planet's inner heat plays a larger role, and that what we see at the surface is only loosely tied to the seasons above. The question remains open. We have only watched Uranus closely for a few decades, which is not even half of one of its years. Neptune's seasons unfold even more slowly. A single season there lasts about 40 Earth years. The planet's tilt is gentler than Uranus, closer to our own, about 28 degrees. So, in theory, Neptune should have seasons more like ours, only stretched out by time. And in some ways it does. Astronomers have watched its southern hemisphere brighten slowly over the decades, as that part of the planet leans toward the distant sun. But Neptune also pulses with its own inner energy. It glows with more heat than it receives from sunlight. This makes its weather strange and unpredictable, full of storms that appear and vanish on timescales we do not fully understand. One possibility is that the slow seasonal change works together with this internal heat to drive long cycles of storms. Another is that the storms follow their own rhythm, almost independent of where the sun happens to shine. We do not yet know which idea is closer to the truth. What makes all of this so hard to study is simple. We have not been watching long enough. Sharp telescope images of Uranus and Neptune only stretch back a few decades. To see a full Neptune year, we would need to observe carefully and continuously from the late 1800s to the present day. And we did not have the tools. Even now, with the most powerful space telescopes, we are catching only a slice of one of these distant years. There is something quietly humbling about that. The ice giants are turning through their seasons, whether we watch or not. Light is creeping across hidden poles. Clouds are forming, drifting, and fading in patterns no human will ever see complete. By the time Neptune finishes the year it began the day it was discovered, generations of astronomers will have come and gone, each one passing the observations on to the next. So the change is real, but it is slow. So slow that it asks for patience we do not always have. Somewhere, right now, sunlight is touching a part of Uranus that has been dark for 20 years. A storm is rising in Neptune's quiet blue. We will not see most of it. We can only sit with the knowledge that the change is happening far away in its own unhurried time. Only one spacecraft has ever visited the ice giants. Just one in all the long history of space exploration. Its name was Voyager 2, and it carried no human aboard. It was a small machine, about the size of a compact car, with a wide dish antenna pointed always toward home. It left Earth in the late summer of 1977, and it is still flying today, far beyond the planets, in the cold quiet between the stars. When Voyager 2 reached Uranus in January of 1986, it had already been traveling for more than 8 years. The world it found was unlike anything seen before. The pictures it sent back showed a pale blue-green sphere, almost featureless, almost smooth, glowing softly in the weak sunlight that far from the sun. The cameras strained to catch any cloud, any band, any swirl. There was very little. Uranus seemed to be holding its secrets close, wrapped in a hazy veil of methane. The light at that distance is faint, The sun from Uranus looks like a very bright star, not a warm disk. Voyager's cameras had to take longer exposures to catch any detail at all. Engineers back on Earth invented new tricks to keep the spacecraft steady during those long shots, turning the whole craft slowly to follow its targets. Like a careful hand holding a candle in the dark, the images that came back were quiet and dim, but they were enough. They showed rings no one had ever clearly seen. They showed moons with cracked and shattered faces. They showed a magnetic field that pointed in a strange, wrong direction. Then Voyager 2 moved on. It used the gravity of Uranus to bend its path further outward, and it kept flying for 3 more years, alone through the dark. In August of 1989, it reached Neptune. Neptune surprised everyone. Where Uranus had been pale and quiet, Neptune was a deep, vivid blue, marked with bright white clouds and dark storms. The light there was even fainter, only about 1,000th of the sunlight we feel on Earth. And yet the planet glowed with motion. Wind streaked across its face at speeds no one had predicted. A great dark oval, the size of our whole planet, drifted slowly through its southern half. Voyager caught it all with its small, patient cameras. The light Voyager saw at Neptune was a strange kind of blue. The methane in the upper air swallowed the red wavelengths of sunlight and let the blue ones scatter back out. So the color we see in those pictures is, in a way, the color of what is missing. The red light went in and never came back. Only the blue returned to the camera. Whether the deep richness of Neptune's blue comes from methane alone, or from some other compound we have not yet identified, remains an open question. Some researchers wonder if a thin haze layer makes Uranus look paler than its cousin. Others think the difference may run deeper into the chemistry of the clouds themselves. Voyager 2 spent only a few hours close to each ice giant, a few hours after years of travel, to gather almost everything we know. Every textbook image of Uranus and Neptune, every careful diagram of their rings, every map of their tilted magnetic fields traces back to those brief encounters. No other spacecraft has returned. No other eyes have looked closely since. The little probe kept going, It passed Neptune's largest moon, Triton, and turned its cameras toward that strange icy world, catching plumes of dark material rising from its surface. Then it sailed onward, out past the last planet, out into the long, quiet beyond. It is still out there now, more than 15 billion miles from the sun, carrying a golden record of sounds and images from Earth. It speaks to us faintly, through a signal that grows weaker each year, and the ice giants wait. They have been waiting for more than 30 years for another visitor. In all that time, the seasons on Uranus have barely shifted. Neptune has not yet completed even a fifth of a full orbit since Voyager passed. The dark spots have come and gone. The winds have kept blowing. The rings have kept turning, soft and faint, in light too dim for us to see clearly from home. Everything we believe about these worlds rests on that single brief glimpse. What Voyager missed, we have not yet found. What it could not see clearly, we still cannot see. The light it gathered was the only light we have ever held from those distant places, and it is, for now, the only light we have. Two worlds born of the same cold outer reaches, made of much the same stuff, swirling through the same kind of frigid sky. And yet, when we look at them side by side, they do not match. Uranus shows a pale, soft cyan, almost milky, like a teacup of water with a single drop of blue ink stirred in. Neptune burns a deeper, richer blue, the color of a still lake at dusk. For decades, this difference puzzled everyone who studied them. They should look like twins. They do not. The question of why has no fully settled answer. But there are sounds, in a sense, woven into this mystery, not sound that travels through empty space, of course, since space carries no air to vibrate. The sound comes from the atmospheres themselves, and from the instruments that turn faint signals into something our ears can almost imagine. Inside the clouds of both planets, winds move at tremendous speed. On Neptune, those winds can race faster than the speed of sound on Earth. If you could float there in some impossible balloon, you would hear a low, endless roar, like standing beside a waterfall that never ends. The hiss of methane crystals brushing past, the deep thrum of pressure building far below, a ceaseless, soft thunder rolling through layers of haze. Uranus would sound different. Its winds blow strong, but its upper air seems quieter, more sluggish in places, with long, calm stretches between the storms. The atmosphere there moves like a slow exhale. If Neptune sings in a deep baritone, Uranus murmurs in a hush. And it is in that very difference of motion that scientists believe the color mystery may hide. One leading idea, proposed only in recent years, suggests that both planets have a thin layer of haze high in their atmospheres. This haze is made of tiny particles, drifting like fog over the deeper clouds. On Neptune, the haze layer appears to be thinner, perhaps because Neptune's stronger churning weather pulls those particles down and clears them away. On Uranus, the air moves more gently, so the haze builds up, thickens, and gives the whole planet that washed out, paler look. Like a window with dust on it, softening every color behind. It is a beautiful idea, but the question remains open. Other researchers wonder if differences in the methane content of the upper clouds play the larger role. Methane gas absorbs red light, leaving blue light to scatter back to our eyes. If Neptune simply has slightly more methane in the right places, or arranged at the right depths, that could explain the deeper hue all on its own. Both theories may be partly right. Both may be missing something we have not yet thought of. When spacecraft and radio telescopes listen to Neptune and Uranus, they pick up other signals too. The magnetic fields of both planets crackle and hum, and scientists translate those signals into audio for study. The result is haunting. Uranus, when its radio emissions are converted to sound, produces a strange whistling chorus, rising and falling, like wind moving through an empty canyon. Neptune's converted signals carry a similar eerie music, with deeper tones, slower pulses, almost like a heartbeat heard underwater. These are not true sounds. They are radio waves, electromagnetic ripples, reshaped so our ears can grasp them. But they remind us that even the silent worlds have voices if we know how to listen. And inside both planets, deeper still, scientists suspect there is real sound. Pressure waves moving through the slushy mantle, vibrations in the layer where water ammonia, and methane mix into a hot, dense fluid. We cannot hear those waves. No probe has ever reached that depth. But the physics says they must be there, rumbling like the slow groan of a sleeping creature, far below the clouds. Perhaps the color difference between the two worlds connects to those deep motions as well. If one planet stirs more vigorously from within, it may push more material upward, changing the haze, changing the clouds, changing what our telescopes see. The blue we observe from across the solar system may be a faint signature of music we will never hear, written in pressure and heat that no eye can witness. For now, when you look at images of Uranus and Neptune side by side, sit with the small wonder of it. Two near twins, painted in slightly different shades, for reasons we are only beginning to guess at. The haze theory, the methane theory, the slow weather theory, each one a quiet hypothesis, each one waiting for better data. The blue and the paler blue drifting through the dark, whispering a question we have not yet learned to answer. There is a quiet kind of arithmetic at the heart of every planet. It begins with how much heat a world makes inside itself and how much heat it gives back to space. For most planets, the numbers come close to matching. What goes out should be roughly what comes in from the sun, plus a little leftover warmth from the planet's own slow cooling. When you write the equation on paper, it looks balanced and calm, like a careful set of scales. For Neptune, the scales tip in a strange direction. Neptune sits about 30 times farther from the sun than Earth does. The sunlight that reaches it is faint, only about 1/900th of what falls on our own world. And yet, Neptune glows back into space with more energy than it receives. The measurements taken by Voyager 2 suggest Neptune radiates roughly 2.5 times the heat it absorbs from sunlight. The math is simple. The meaning is not. Uranus tells a different story, and that difference is its own puzzle. Uranus gives off almost exactly what it takes in. The internal heat leaking from its core is so small it sits near the edge of what we can measure. Two planets of nearly the same size, born from the same cold outer disk, made of similar ices and gases, end up with wildly different inner furnaces. One quietly burns. The other seems to have gone cold. The numbers behind this are elegant in their own way. A planet's heat budget can be written as a balance between absorbed sunlight, reflected light, and emitted infrared glow. Astronomers measure the brightness in visible light, then measure the warmth in infrared and compare. For Neptune, the ratio comes out near 2.6. For Uranus, it sits close to 1, perhaps as low as 1.06. Same equation, same kind of world. Two answers that should not be so far apart. One idea is that Uranus suffered a great blow long ago. The tilt of its axis, lying almost on its side, suggests a giant impact in the early solar system. Such a collision may have stirred the planet from top to bottom, releasing its inner heat all at once into space. After that early venting, Uranus would have cooled faster than its sibling, and today we would see a planet that has already given up most of what it once held. The math fits, but the evidence is incomplete. Another possibility is more subtle. Inside an ice giant, layers of different materials may settle into a stable order, with heavier ices below and lighter gases above. If those layers do not mix, heat from the deep interior cannot rise easily to the surface. The planet becomes its own insulator. Some researchers wonder if Uranus has settled into such a layered state, trapping its warmth far below, while Neptune still churns and stirs, letting its inner heat flow out. The same equations describe both planets, only the boundary conditions differ. There is a deeper beauty in how predictable the outer numbers can be. The orbits of Uranus and Neptune are known to extraordinary precision. We can say where each planet will be decades from now, down to a small fraction of its width. Neptune takes about 165 Earth years to complete a single trip around the Sun. Uranus takes about 84. Those numbers come from Kepler's old, simple rules, written long before anyone knew these worlds existed. The rules still hold out there in the cold. And yet, the same mathematics that predicts their motion so cleanly cannot tell us why one glows warmer than the other. The orbits obey gravity, which is a tidy law. The interiors obey thermodynamics, convection, chemistry, and history, which are tangled together. The equations exist. The inputs do not. We do not know the exact composition of either core, or how the layers are arranged, or how much heat was trapped at birth. So, the inner heat of the ice giants becomes a quiet question written in numbers. 2 planets, nearly the same size, nearly the same distance, nearly the same color. One radiates more than twice what it absorbs. The other barely radiates anything extra at all. The ratio between them, somewhere near 2.5 to 1, is a small number that hides a large mystery. Perhaps Uranus was struck and emptied. Perhaps Neptune still stirs while Uranus has gone still inside. Perhaps both planets follow rules we have not yet written down. The math is patient. It will wait. Somewhere in those gentle equations, balanced between sunlight and infrared, between gravity and heat, lies an answer we have not yet found. For now, the scales sit uneven, and the 2 pale worlds keep their warm and cold secrets to themselves. The solar family we see tonight may not be the one that first formed. Some of the strongest clues come from the ice giants themselves. Uranus and Neptune sit far from the sun, in a region where the early disk of gas and dust was thin and slow. Building 2 worlds of their size out there in the time the solar system had is surprisingly hard to explain. The material was simply too spread out. The orbits were too long. The clock was ticking too fast. This puzzle has led many researchers to a quiet but striking idea. The ice giants may not have been born where we find them now. They may have formed closer in, somewhere between the orbits of Jupiter and Saturn, where the disk was richer and the building blocks more plentiful. Then, slowly, over millions of years, gravity from the larger gas giants may have nudged them outward. If this is true, the calm worlds we see today were once travelers, drifting through the early solar system like leaves carried on a slow river. One version of this idea is sometimes called the Nice Model, named after the French city where it was first worked out. In this picture, the 4 giant planets once orbited much closer together. A long, gentle dance with a belt of icy debris pulled them into new paths. Jupiter drifted slightly inward. Saturn, Uranus, and Neptune drifted outward. Uranus and Neptune may have even swapped places along the way, with Neptune ending up farther from the Sun than the world that helped push it there. It is a strange thought. The order we take for granted may be an accident of timing. Other researchers favor different versions of the story. Some think the migration was slower and gentler, with no dramatic swap. Some think there may have been a fifth giant planet long ago, one that was flung out of the solar system entirely during the shuffle. That lost world, if it ever existed, would now be drifting alone in the dark between the stars, cold and silent. Whether it was ever real remains an open question. The evidence is indirect, written in the orbits of distant objects and the scars on ancient moons. What makes this idea so quietly remarkable is how delicate it all seems. If the early giants had moved a little faster or a little slower, the inner solar system might look nothing like it does. The gentle rain of icy bodies that struck the young Earth, possibly delivering some of its water, may have been a side effect of that migration. Change the timing, and the rain falls in a different pattern. Change the masses, and the Earth might never have settled into the steady orbit it holds today. The warm, blue world beneath your roof tonight may owe part of its calm to a long ago shuffle in the outer dark. The same fragile balance shows up in smaller details. The tilted spin of Uranus, the captured orbit of Triton around Neptune, the strange gaps in the asteroid belt, the icy crowd of objects beyond Neptune, known as the Kuiper Belt. All of these features fit together more naturally if the giants once wandered. Each one is like a footprint left in soft ground, hinting at a path the planets took long before any eye could see them. Still, the picture is not complete. The models can produce solar systems that look like ours, but they can also produce many that do not. Small changes in the starting conditions lead to very different endings. Some researchers wonder whether our arrangement is common among stars, or whether it required a rare run of luck. The growing catalog of planets around other stars suggests that ice giants may be quite ordinary in the galaxy, yet the precise dance that placed ours in their current orbits may be far less ordinary than it seems. There is something soothing in this uncertainty. The worlds we see tonight, steady and slow in their long orbits, may carry within them the memory of a much more restless youth. Uranus tipped on its side, Neptune far out in the cold, both possibly born elsewhere, both possibly nudged into place by forces that have long since quieted. The solar system around you may be the calm after a very old storm. We do not know for certain how much the ice giants wandered, or when, or why their paths settled where they did. The clues are scattered across moons and rings and distant icy bodies, and the story is still being pieced together. For now, it is enough to imagine those two pale blue worlds drifting outward through a younger sky, finding the quiet orbits where they have rested ever since. Somewhere beneath the pale blue clouds of Uranus, and somewhere beneath the deeper blue of Neptune, there may be oceans. Not oceans like the ones on Earth, with waves and shorelines and salt spray. These would be hidden seas, buried under thousands of miles of crushing gas. They would be warm, dark, and stranger than anything we know how to picture. And we are not yet sure they exist. The idea begins with what we cannot see. When we look at Uranus and Neptune, we only see the tops of their clouds. Below that thin layer, everything is guesswork shaped by physics. Models suggest a thick blanket of hydrogen and helium near the top. Beneath that, the pressure climbs to numbers our minds struggle to hold. And somewhere in that crushing middle, water and ammonia and methane may pool together into a vast, warm fluid. Some researchers call this layer the mantle. Others call it the ocean. The two words point at the same mystery, but carry different feelings. A mantle sounds solid and slow. An ocean sounds wet and alive. The truth may sit between them, in a state of matter that has no clean name on Earth. This hidden fluid would not be calm. The pressure deep inside an ice giant is so strong that water stops behaving the way it does in a kitchen pot. It may turn into something called superionic ice, where the oxygen atoms lock into a solid lattice, while the hydrogen atoms flow through them like a liquid. A material that is solid and liquid at the same time. Laboratories on Earth have created small flashes of this strange ice. but only for fractions of a second. Whether vast layers of it slosh inside Uranus and Neptune remains an open question. If those layers exist, they may help explain the tilted, lopsided magnetic fields that puzzle us so deeply. A flowing salty fluid can carry electric currents. Electric currents can generate magnetism, so a hidden ocean, churning slowly in the dark, might be the engine behind those crooked field lines we can measure from far away. One theory points to a thin shell of conducting fluid near the surface. Another imagines a deeper, broader sea. Both ideas remain on the table, and neither has been ruled out. The word ocean carries other thoughts as well. On Earth, oceans mean life. On the icy moons of Jupiter and Saturn, possible buried oceans have become some of the most exciting places to search for living things. So it is natural to wonder about the inner seas of the ice giants. Could anything stir there? Could chemistry of any kind unfold in that hot, dense soup? Most researchers think the conditions are far too harsh. The pressure alone would crush familiar molecules into shapes biology could not use. Yet the question lingers, soft and unanswered, simply because we cannot reach down and look. There is also the matter of the moons. Triton, circling Neptune in its strange backward orbit, may carry an ocean of its own. Tidal forces from Neptune could warm its interior just enough to keep a layer of liquid water beneath the icy crust. Some of the larger moons of Uranus, including Titania and Oberon, might do the same. The evidence is faint. It comes from the way their surfaces look in old photographs, from cracks that hint at past flexing, from the simple math of how heat moves through ice. None of it proves an ocean. All of it leaves the door open. What makes this mystery so gentle is how much it depends on patience. We cannot drill into a gas giant. We cannot send a submarine through a frozen moon. The answers will come slowly, through better telescopes, better models, and one day, perhaps, a spacecraft that lingers in orbit instead of flying past. Each measurement will narrow the possibilities a little. Each generation of researchers will inherit a sharper version of the same question. For now, the ice giants hold their secrets quietly. We can sketch their interiors in soft layers of color. Label the regions where oceans might live, and admit that the labels are guesses. We can imagine warm, dark seas folding slowly beneath impossible pressure. And we can also imagine that those seas may not exist at all, that the interior may be something even stranger that we have not yet named. That uncertainty is not a failure. It is an invitation. Two worlds at the edge of our solar family still have rooms we have never entered. The lights are off inside. The doors are closed. And somewhere behind them, perhaps, the slow murmur of hidden water moves in the dark, waiting for a future curious enough to listen. For most of human history, our two ice giants felt like the only ones of their kind. They were strange siblings at the edge of our small family of worlds, and we had nothing to compare them to. That has changed in the last few decades. Telescopes, both on the ground and in orbit, have begun to find planets around other stars. Thousands of them now. And among those distant worlds, a surprising number seem to be the size of Uranus and Neptune. Astronomers have a quiet name for them. They call them sub-Neptunes, or mini-Neptunes when they are a little smaller. These planets sit in a size range between Earth and our gas giants. They are common. In fact, they may be among the most common kinds of planets in the galaxy. That alone is a gentle surprise. The shape of our own solar system, with its rocky inner worlds and its giant outer ones, may not be the usual pattern at all. What these distant ice giants actually look like is mostly unknown. We see them only as tiny dips in starlight, or as faint wobbles in the motion of their stars. From those small signals, we can guess their size and their mass. We can sometimes estimate how dense they are, but we cannot see their clouds. We cannot map their storms. We do not know if they shine in blue or green, or some color we have not imagined. Some of these worlds orbit very close to their stars. They circle in just days, baked by heat we would find unbearable. Others drift far out in long, slow paths, much colder than Neptune. A few seem to be wrapped in thick hydrogen air. Others may be water worlds with deep oceans hidden under heavy steam skies. The variety is wider than anything our own solar system shows us. One open question is whether these planets formed the way Uranus and Neptune did. The story we tell about our own ice giants involves a slow gathering of ice and rock in the cold outer disk around the young sun. But many of the distant sub-Neptunes sit too close to their stars for that story to work. Some researchers wonder if they formed far out and then drifted inward over millions of years. Others suggest they grew where we find them, from material that behaves differently than we expected. The question remains open. There is another puzzle hiding in the data. When astronomers sort these small worlds by size, they find a strange gap. Planets a little larger than Earth are common. Planets a little smaller than Neptune are common. But in between, there is a quiet thinning out, a missing slice in the size chart. One idea is that some young sub-Neptunes lose their thick air to the heat of their stars and shrink down into bare rocky cores. Another idea is that they were never quite the same kind of world to begin with. We do not yet know which story is right. If even one of these distant ice giants could be studied in detail, it might tell us things our own two ice giants have kept secret. We might learn how often diamond rain happens out there, if it happens at all. We might learn whether tilted magnetic fields are common, or whether ours are unusual. We might find that Uranus and Neptune are typical members of a great galactic family. Or we might find that they are stranger than we ever guessed. In 1,000,000 years, our telescopes will be different. In 1,000,000,000 years, the sun itself will have grown larger and hotter, and our ice giants may have changed in ways we cannot easily picture. The cold outer reaches of our system may warm. New ices may melt. New skies may form. And by then, the planets we study tonight around other stars will have moved through their own slow lives, some swallowed by their suns, some drifting free into the dark between stars. The universe keeps making ice giants. Somewhere right now, in a young disk of dust around a newborn star, the seeds of another Neptune are pulling themselves together. Somewhere else, an old ice giant is slowly losing its outer layers as its star swells with age. The pattern repeats with quiet variations across the long reach of time. We do not know yet where our own ice giants fit in this larger story. They might be ordinary. They might be rare. They might be the cool, dim cousins of worlds we have not even imagined. The pale blue light of Uranus and Neptune may be one common note in a great unheard song, or it may be something almost unique in this corner of the galaxy. For now, the question drifts gently with them, out there at the edge. For all the wondering we have done across these long, quiet hours, almost everything we know about Uranus and Neptune comes from a single brief visit decades ago by one small machine. One flyby of each world, a few days of close looking, then silence again. The ice giants have been waiting ever since, turning slowly in the dark, holding their answers close. And so the people who study them have spent years dreaming up the next visit. Not a flyby this time, a real one. A spacecraft that would arrive, slow down, and stay. The dream most often spoken of is an orbiter, a patient machine that would loop around one of these worlds for years, watching the seasons shift, mapping the strange magnetic field from every angle, listening to the deep churn beneath the clouds. Some plans focus on Uranus because its sideways tilt makes it the stranger of the two, and because the timing of its long seasons lines up well with a launch in the coming decade. Other plans favor Neptune with its furious winds and its captured moon Triton, which may hide an ocean of its own. Both ideas remain open. Neither has been built. For now, they live only in quiet reports and patient drawings. Alongside the orbiter, many of these dreams include a small probe, a second craft, no larger than a barrel, that would drop away from the main ship and fall through the clouds. It would feel the wind on its skin and taste the air as it sank. It would send back numbers no one has ever seen. The true mix of gases deep inside an ice giant. The temperature curve going down. The way the pressure climbs toward something almost beyond imagining. The probe would last only an hour or two before being crushed. But in that hour, it would tell us more about the inside of these worlds than every telescope ever built. We do not know if either mission will happen in our lifetime. The distances are vast. A spacecraft sent today would need more than a decade just to arrive. The funding is uncertain. The engineers who would build it are still being trained in schools. And yet the dream stays alive because the questions stay alive. What lies beneath those calm blue clouds? Why the magnetic fields tilt the way they do? Whether diamond rain is real, whether Triton's quiet surface hides a sea. The ice giants are the last great unexplored places in our own solar family, and something in us cannot quite let that be. Step back now, as far as the mind will go. These two worlds, turning at the cold edge of the sun's reach, are made of the same things you are made of. The hydrogen in their deep oceans was forged in the first minutes after the universe began. The oxygen woven into their ices was cooked inside ancient stars that lived and died before our sun was born. The carbon that may fall as diamond through their hidden layers came from the same kind of stellar furnace that made the carbon in your bones, in the wood of the tree outside your window, in the ink of every book you have ever read. We are kin to Uranus and Neptune in a literal way. The same atoms, the same long history, different addresses in the same family. When a star ends its life and scatters its outer layers into the dark, those atoms drift for millions of years before gathering again into a cloud, a disk, a world. Some of them become planets like ours, warm and lit. Some become ice giants, quiet and blue and far. Some become moons, comets, the dust between the stars. All of it is the same material, sorted by chance and gravity into different shapes. The mystery of Uranus and Neptune is, in a small way, the mystery of yourself, asked in another voice and at another temperature. And so, the dream of going there is not really about machines or budgets or launch windows. It is about wanting to know the rest of the family, wanting to put a hand, even a metal one, on the cold edge of the system and feel what is there. The ice giants do not know we are wondering about them. They simply turn and drift and glow faintly in the dark, the way they have for billions of years. Whether we ever reach them again is still uncertain. The plans exist. The will is gathering. The answer is not yet written. For tonight, the question is enough, and the quiet is enough, and the slow blue light of those distant worlds is enough to carry you gently towards sleep. And so come to the quiet end of our long visit to the outer dark. The ice giants are still out there, of course. They have not moved in any way you could feel. Uranus is rolling slowly on its side, the way it has rolled for billions of years. Its pale blue-green face turned partly toward a sun that looks no larger than a bright star. Neptune is drifting along its long, slow path, its deep cobalt clouds shifting in winds we still cannot fully explain. Picture them for a moment, the way you might picture two distant lanterns at the far end of a quiet hallway. One tilted on its side, almost lying down as it spins. The other upright, deep blue, marked here and there by white wisps of methane ice. Both of them turning in a silence so complete that no sound from any world could ever cross the distance between them. The sun shines on them, but only barely. A single ray of sunlight takes more than 4 hours to reach Neptune. By the time it arrives, it is faint and cold, more memory than warmth. And yet, they are not empty places. Deep inside them, oceans of hot, strange water may be churning. Layers of slushy ice and ammonia may be sliding past one another in patterns no one has ever seen. Diamonds may be falling slowly through hidden seas. Magnetic fields may be tilting and tumbling in ways that still puzzle the people who study them. None of this stops just because we have stopped looking. The mystery keeps unfolding in the dark, whether or not anyone is watching. There is something gentle about that thought. The universe does not need us in order to be wonderful. It was wonderful long before there were eyes to see it. It will be wonderful long after this night, this room, this quiet moment have passed. The ice giants will keep their secrets a little longer, and that is all right. Some questions are meant to be lived with, not answered. Some mysteries are meant to be held softly, the way you might hold a smooth stone in your pocket, turning it now and then without needing to know exactly what it is. You have learned a great deal tonight, or perhaps you have drifted in and out, catching pieces of the story here and there. Either way is fine. The facts will still be there tomorrow. The open questions will still be open. Uranus will still be tilted. Neptune will still be blue. The winds will still be racing across cloud tops no human has ever stood beneath. And somewhere, possibly, beneath the frozen crust of a small moon called Triton. A hidden ocean may be rocking gently in the dark, lit only by the faint glow of its own slow heat. Imagine that ocean for a moment as you let your thoughts slow down. A sea of liquid water sealed beneath miles of ice, untouched by any sun. The water is still. The ice above is still. The stars overhead, if you could see them, would be still as well, sharp and unblinking in a sky with no air to soften them. Whether anything swims in that hidden sea, no one knows. The question waits, patient, in no hurry to be answered. Far beyond Triton, beyond Neptune, the solar family begins to thin out into the long quiet of the Kuiper belt, and then the even longer quiet beyond. The ice giants stand at the silent edge of all that, the last large worlds before the dark grows truly deep. They are the doorkeepers, in a way. The final pale lanterns at the threshold of interstellar space. And they are spinning, even now, as you settle deeper into the soft place where sleep begins. There is no need to hold on to any of it. Let the facts fade. Let the theories blur. Let the picture of those two distant blue worlds soften into something dreamlike, something you can carry into sleep without effort. The universe is vast, and it is gentle with those who pay it quiet attention. You are small inside it, and that smallness is a kind of comfort. You are held by gravity, by air, by the slow turning of a warm planet that knows how to keep you safe through the night. We may learn more about the ice giants in the years ahead. We may not. Either way, they will keep turning, and the question of what lies inside them will keep waiting kindly for whoever wants to wonder about it next. For tonight, the wondering is enough. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.